Okay, so for those of you who don't know me, my name is Joe Winston. I'm the nTopology account manager here at Measurement Solutions, and today I'm going to give you an introduction to nTopology platform. I'm going to show you a few slides to give you a brief overview of the company and some background of how the software actually works, and then we'll jump into the software itself and I'll show you some live examples of not only what the software can do, but just how quickly and robustly it can perform some really complex operations. So first, a quick background on MSL. We were founded in 1998 and predominantly focused on metrology solutions. In the early years, we built a large customer base with not only CMM equipment, but also support and calibration services. The development of more complex geometries created the demand for 3D scanning, and not just for inspection, but also for reverse engineering. And this is where MSL's relationship with Creaform began. We're the UK reseller for Creaform, and it's enabled us to expand our customer base to over 1,000 UK customers. nTop was really a natural fit with our existing customer base, and it's enabled us to offer an end-to-end solution, from scanning a 3D part to optimizing it in nTopology through to inspection of the final part. So who are nTopology? The company was founded in 2015 and quickly released their first software package called Element. Element was focused on lattice generation and manipulation, and it was aimed to really fill a void where traditional CAD systems fell short in working with these quite complex structures. And nTopology could really excel here because it was based on a new and very unique mathematical architecture. nTopology soon realised that their maths-based approach had advantages far beyond just working with lattices, and it had the potential to provide a whole new way of designing parts based on maths and data. In 2018, nTopology took all of its learning from Element and launched its beta version of Platform. Lockheed Martin were one of the first to see the potential of Platform and got on board with a $3 million investment. As further investments were secured in 2019 and 2020, even more features were added to Platform, giving engineers faster and more efficient tools to work with. So what is nTopology? It's not an easy question to answer because it can't really be compared to the CAD packages that we know of today. To sum it up in one line, we would say that nTopology is a software company building the next generation of engineering design tools for advanced manufacturing. But what does that really mean? As a starting point, I actually find it an easier concept to grasp by explaining what it isn't rather than what it is. So the name nTopology conjures up the idea that it's purely a topology optimization tool, but it's not. Neither is it here to replace existing CAD packages like SolidWorks and CATIA or simulation software like ANSYS. It sits alongside all of these existing packages, allowing you to share data between all of them. And the idea of sharing data is a really important part of nTopology. By playing nice with existing software packages, nTopology is here to create better workflows and help to create complex parts more efficiently and more robustly. So rather than a CAD package, we can think of Platform as an engineering environment where you can combine design, simulation, and manufacturing inputs, allowing a user to consider function, geometry, FEA results, and DFAM all simultaneously. So unlike traditional CAD packages, where we simply create a 3D model, in nTopology we create a process built on the foundations of maths and data. This means that if we create a process to build a heat exchanger or a rocket nozzle, we never have to design another one. We only have to adjust parameters to account for a revised space envelope, for example, and the workflow will automatically generate the new design. So why should we consider nTopology? With the advances of AM machines, materials, and expertise, we now have the ability to manufacture parts that are far more complex than we can effectively design using traditional CAD packages. And it's really in stark contrast to where we were 10 years ago, where we could design parts that we couldn't really manufacture. So what we're saying is that nTopology is bridging the gap that we currently have between design and manufacture. And it's doing this with a smarter and more efficient use of data. So let's break down what I mean by a smarter use of data. When we think of early manufacturing, we think of someone in a factory manually making each individual part. But now we have machines that can create hundreds of parts in a minute. Similarly, computing power continues to evolve year on year, So my watch, for example, has more tech in it than my phone did 10 years ago. And we wouldn't even consider a 10-year-old computer as good enough to design the complex components that today's engineering environments demand. Essentially, we've seen exponential improvements in manufacturing and computing, but design software is somewhat lagging behind, and it's shifted the bottleneck from manufacturing to design. The traditional CAD packages are based on the same architecture as when they came into existence 40 years ago. And you could really go even further than that and say that it's essentially a descendant of pen and paper. Okay, we've moved to a 3D world, but essentially CAD is a 3D version of a historical process, where a designer uses their best guess at how a system should work and creates a drawing for someone else to manufacture. Now, nTopology does things differently, and that's why we really believe it's a next generation design tool. We live in a world where data really is everywhere and it's everything, so why not apply it to designing parts? When we analyse and work with any other data sets, we have automated ways to process it. I can create a spreadsheet in Excel or write a program that someone else can use to solve complex problems. And this is the backbone of nTopology's design philosophy. So with nTopology, rather than using computer-aided design, we're using the technology at our disposal, along with real data, and asking the computer to generate our design. Using computer algorithms, we can automate the creation of optimized shapes that humans wouldn't even dream of. And even if they did, it would take them days, if not weeks, to create. So, nTopology has many unique features that really differentiate it from traditional CAD packages. But there are three key elements that really set it apart. So I'm going to give you a quick intro into each of these three before we dive into them in a little bit more detail. So implicit modelling is where models are based on mathematical functions. Models are very lightweight, making them easy to work with and easy to store. And the geometries are unbreakable. So we can see in this little screen recording below, this is a gyroid structure inside a little engine block being updated in real time. You can see we can adjust the parameters of the gyroid structure and the model is just updating straight away. There are no crashes to do with intersecting faces or radii, just updates straight away. Field-driven design creates the ability to quickly process complex features and operations, and simulation data can be converted into fields, which can drive generative design. The fact that implicit modelling and field-driven design make for such robust models means that we can reuse workflows over and over again. So workflows create a process rather than a description of a 3D model, and it leads to repeatable and reusable customization. So in the screen recording below, we can see some patient-specific CAD data. This has been brought into nTopology, and we're applying a stochastic lattice to the faces of these pieces of CAD data. You can see the models in nTopology are so robust that we can just click on a face, click on a model, and it's going to apply that stochastic lattice to whichever face we tell nTopology to apply it to. So let's get into these three in a little bit more detail. So implicit modelling, it's a lightweight way of representing a 3D object using a mathematical function. Traditional CAD systems use BREP, or body representation, to define or describe a 3D model. It plots edges, faces, and points in space, which is fine for simple geometries, but it gets very complicated very quickly when we start dealing with lattice structures, freeform shapes, and intricate supports that we need for AM builds. With the mathematical architecture of nTopology, what you see on the screen isn't really a 3D model, but it's a graphical representation of a mathematical formula. And because we're just looking at a mathematical formula, the geometries are unbreakable. So intersecting bodies, overlapping faces, and inverted surfaces that we see errors with in traditional CAD packages are really a thing of the past in implicit modelling. So we can think of it as a volumetric way of describing a shape. And in the example on the right here, we can see three identical CAD models. So this model is stored as a mesh. It's 100 megabytes and 4 million triangles. The same model stored as a BREP is 30 megabytes, 2,000 faces. The same model stored as an implicit body is just 70 kilobytes. And this is really scalable as well. So if we were to double the size of this model, if we were to keep the same resolution, the size of the mesh would increase massively. The size of the B-wrap would also increase as we get more faces. But the implicit model would stay at around 70 kilobytes because we're just storing a mathematical formula. Okay, so field and data-driven design. A field is a rule that associates a value to each point of 3D space. So it's the idea that every point in space is represented as a distance, and by using maths, we can assign a positive or a negative number to that point. So in the screenshot below, we can see this is a field taken through the section of a cube. So all of these darker areas here are a negative number, so that represents a solid in nTopology and implicit modeling, and all of these lighter areas are a positive number, and they're just free space. So you can think of this as a balloon analogy. So if we were to fill up a helium balloon in a room, we would have obviously the skin of the balloon filled with helium, and in nTopology we would say that the helium is a negative number, and that represents a solid. The skin of the balloon would be the boundary of the model, and any free air in the room is a positive number, and that's represented as free space within nTopology. And it doesn't really matter whether we're describing the shape of a balloon or the shape of a really complex gyroid structure. All that nTopology is doing is the maths in the background to decide whether the point in space should be represented as a positive number or a negative number, and then it's assigned as a solid or free space. And because we're just dealing with a massive volume of space that's just got a number represented to it, then we can bring in real-world data like displacement values, heat maps, or pressure maps. So reusable workflows. It's the idea that repeatable, reusable, and customizable are no longer mutually exclusive. So a workflow applies specific instructions or commands to a geometry, so the author is building a process rather than a part. So use cases here are medical implants, which we kind of saw a little screenshot of earlier, orthotics and prosthetics, mass customization of maybe athlete-specific helmets, and rapid creation of initial prototypes to speed up time to market. So a few case studies here of where we really see the benefits of nTopology. Heat exchangers, I think they're a huge potential with the combination of AM, nTopology, and bringing in external data. So we can import fluid flow data and heat maps from external software. We can assign a space envelope in nTopology and bring all that data together and get the computer to generate the most efficient heat exchanger that it possibly can. For things like satellite brackets and CubeSats, obviously these things are flying in space, so we want them to be as light as possible. So we can use topology optimization to take out all of the excess material that we don't need. Also use the advantages of additive manufacturing to combine parts into one part rather than building up assemblies. And medical specific devices, which we kind of touched on earlier. So this is a build plate filled with patient specific devices and implants ready for surgery. Okay, so that's pretty much the end of the presentation side of things. If anyone's got any questions at this point, then please feel free to let me know. And if not, we will dive into the demo itself and show you around some of the software. Okay, so let's get into the software itself. So for some, this is going to be your first look at the user interface of nTopology. So like a traditional CAD package, we have a tab along the top here with a series of tools. We can create some primitive shapes, do some modeling, so some Boolean unioning, extruding, revolving. We can create lattice structures from here. We've got a simulation tab. Got a specific additive manufacturing tab. We'll get into all of these in more detail a bit later on. On the left here, rather than a design tree, we have what we call a notebook. And in this notebook, we have a series of blocks. Each of these blocks is an individual instruction or process, and a series of blocks builds up a workflow. So we have a workflow here, which is going to take whichever model that we drop into this block here, turn it into a gyroid and turn it into a lattice. So if I drag and drop my cube into the top of this mini workflow, we're going to really quickly turn it into a lattice structure and into a gyro structure. And it doesn't matter which model you put into the top of this workflow, nTopology is just going to do exactly the same process, follow the same workflow for each part. So you can see here with the speed of implicit modeling how quickly we can turn this solid bracket into a gyro structure and into a really complex lattice structure. Okay, so to go back to the view that we started with, these are 3 identical models. This is the same bracket. So the bracket was imported in as a step file. So this is in brep version. So you can click on faces, you can click on edges, and we can click on points, as we'd expect from a brep model. This has been converted into an STL file within nTopology. This is now converted into triangles, so it can be exported into another software or exported to build. And we can also convert the step file into an implicit model, which this is here. So we can't click on the edges and faces like we can in the brep, but we can now do some really complex operations really quickly with this model, like you saw when we turned it into a gyroid structure and into a lattice structure. So let's take a look at these simple shapes that we've created in nTopology, a cube and a sphere. If I take my cube and run a section through it, you can see it's a completely solid cube. Now if I show my field, as we saw earlier, we've got these same colours and the same pattern. So on the boundary of the model, we have 0 value. Anything inside the model is a negative number. Anything outside of the model, outside of the solid, is a positive number. It gets progressively bigger as we get further away from the boundary of the model. See the same thing with this sphere. If we run a section through it, you can see it's completely solid. If we show the field, you can see the same thing again. We have negative numbers inside the solid, going out to 0 value at the boundary, a positive number getting progressively bigger as we get further away from that boundary. Okay, so we've got another little workflow here that I'm going to run you through. So in this workflow, we take an implicit body. In this case, we've taken the cube, we've shelled it. As you can see, it's now hollow. We've taken the inside of that cube, the void of the shell, and we're going to convert it into a lattice structure. From here, we're going to merge it into the cube. Now we've got a cube that's hollowed and filled with a lattice structure. Now all of these intersections between the lattice and the inside of the shell, we have a sharp corner. The resolution of the screen here doesn't quite show how sharp it is, but it is truly a sharp corner. Now, in a traditional CAD package, if we wanted to put the radius on all of these intersections, it would take us quite a while to go in and click all of those individual faces, turn those into radiuses. In nTopology, we have an option here. We just click the blend radius that we want. In this case, I want a 0.5 mm blend radius, and in less than a second, it's going to convert all of those sharp corners to a nice radius. To show you how quickly it updates, you just select whatever blend radius we want. We're never going to get intersecting surfaces that's going to crash and cause rebuild errors. Even if we pick a silly number, 20 mm blend radius, we're still going to get a result. We're not going to get any crashes. Okay, so this cube is just a 10 mm cube, but if we turn this from a 10 mm cube into a 50 mm cube, we've now got a much bigger structure that we're starting with. But because we've built a workflow here, nTopology is just going to run through the same process again. So it's going to shell it, it's going to take the inside, it's going to turn that inside into a lattice structure, it's going to merge everything together, and here we have our final part. So rather than the first model, 10mm cube, it was 27 units of lattice. Now at 50mm cubed, it's about 12,000 units of this lattice. And we can still control this blend radius just as quickly. So I can change that from 0.5 to 2mm, and in less than a second it's going to update all of the blend radiuses all the way around the part, everywhere that it's intersecting between the lattice and the shell. Now we can really quickly update this as well. So I can change the lattice type, I can change the cell size, and I can change the beam thickness. And because we've built a workflow rather than just a part, I can take my cube out of the top of the workflow. Instead, I'm going to drag and drop my sphere. It's going to run through that exact same workflow again, hollow it and put a lattice structure inside. Now the cube and the sphere are quite simple parts. What if I were to drag and drop my bracket into the top of this workflow? So a completely different part, very different design, very different shape, but it has done exactly as we would expect and shelled it, filled it with that same lattice. Now the beam thickness that we have the option of changing here has this little Wi-Fi symbol on it. This Wi-Fi symbol gives us kind of an all-access pass to loads of different design options. It means we can drive this value based on some field data. So in this case, I am going to drive the beam thickness. Just going to get it in the right orientation so we can see. So I'm going to drive this beam thickness to say that I want a thicker beam thickness at the top of the model and a thinner beam thickness at the bottom. Maybe we want to distribute the weight more evenly in the z-axis, or maybe we just know that this is an area of high stress and we want a bit more support and rigidity up there. So all I have to do for this is add a ramp block. I'm just going to type ramp and add in a ramp block to my notebook. Now I'm going to drive this from a plane. So I'm going to insert a plane from normal. I'm going to put the plane down at the bottom of the part here. I'm going to say at 0mm from the plane, I want my beam thickness to be 1mm, and at 75mm from the plane, so somewhere up here, I want my beam thickness to be 3mm. I'm going to change that with geometric continuity, and all I'm going to do is drag and drop my ramp block into my beam thickness, and it's going to give us a result where the beam thickness is much thinner at the bottom here. They gradually change to a thicker beam thickness at the top here. So this is just kind of a concept of how quickly we can vary those beam thicknesses. So let's put it into a more real-world application. So here we've got a brake pedal. Again, it's been imported as a step file. So we've got the option to click edges and faces, and I've separated it out here. So we've got the kind of the outer frame of the brake pedal and this cavity, this inner section. What I want to do is keep this outer section, keep this frame, but convert the faces in here. All of this body I want to convert into a lattice structure. But I want to do it with a continuous lattice between these two faces. So here I've split out the two faces that I'm going to use. I've created a cell map between the two that's conformal between the two faces. I've also selected a unit type, and when I merge these together I can create a lattice that's conformal between those two CAD faces. And when we merge this together at the end, we have a lattice within the frame of this brake pedal. We've got loads of control over this lattice. We can change the lattice type really quickly, whatever we want to. we can change the unit count. So if we want a bigger unit count in this axis, we can just update that to make a more dense lattice structure. We've also got control over the beam thickness, so I can change that to a uniform 4mm, back to 2mm, and again we've got control over this blend radius between the lattice and the body that we're joining it to. At the moment it's 2mm, take that to 4mm, really quickly change that blend radius to whatever we want it to. So in a traditional CAD package, this is potentially quite a complex task to add this lattice structure in, but in Topology we're kind of only just getting started here, because you'll see again the beam thickness, we've got the Wi-Fi symbol, so we can change this beam thickness based on some data. Now I could change it so that it's thicker at this end and thinner at this end, but what probably makes more sense is to have a thicker beam thickness in areas of high stress and a thinner beam thickness in areas of low stress. So to do this, I'm going to run a static analysis on the part. So we're going to take our original brake pedal, we're going to mesh it, assign a material, assign a displacement restraint, which is going to be in on this hole here. I'm going to apply a force to the top of the brake pedal, and the force is acting down on the pedal. So the results of our static analysis are here. We can see the areas of high stress are concentrated up here, and then these blue areas show our areas of low stress. Now I want to use these to drive our beam thickness. So again, I'm going to need to create a ramp block. But this time, rather than using a plane, my scalar field is going to be my von Mises stress, and at areas of low stress I'm going to just copy and paste this number here and say that in areas of low stress I want my beam thickness to be 0.75mm, and in areas of high stress here, just copy and paste that, I want my beam thickness to be 3mm. Now all I have to do is drag and drop this ramp block into my beam thickness up here. Now if we look at our final part again, we're going to see a result where we have much thicker beams in these areas of high stress here, much thinner beams in areas of low stress over here. Now to give another example of some real world data and how we can fine tune lattices based on that, I'm going to use the example of this seat. This seat, we've set up a static analysis in nTopology, and now we have our areas of high stress shown in red and areas of low stress over here. As we'd expect, the areas of high displacement are where the sit bones would normally be on a saddle, and we can use this data to drive the lattice density. So we've set up this lattice within the body of the seat. We've said that in areas of high displacement we want a much denser lattice structure, and again we can use that same data to drive our beam thicknesses as well. So we're saying that in areas of high displacement we want a thinner beam thickness to give a bit more cushioning. In areas of low displacement the beams can be much thicker. And now we can merge this together with some of the surfaces that we want to keep to give us a perfectly optimized bike saddle. Let's take a look at this one. So again, we have a step file that we've brought in. This is an automotive bracket. So this is the main body of the bracket here, and the connections that go from and to this bracket. So we're going to convert the bracket into an implicit body, and we're going to separate out our interface regions. So anywhere that the bracket interfaces with these sections that come off it. We are going to convert our bracket into a mesh ready to run an FEA analysis and our topology optimization. The first thing we've done here is run a static analysis to see where the areas of high stresses are. And we're going to run it through a topology optimization, and here are our raw results from our topology optimization. So you can see that some of the surfaces are a little bit rough, not so smooth, so not ideal for 3D printing. but we have a block in Topology to smoothen our result, the smoothen body block. When we click that, we get a really nicely smooth surface and a nice organic shape. You can see we've lost some of the interface regions, but because we split them out earlier, we can really quickly Boolean union them back together and create our topology optimized part with the nice crisp interfaces. So from here we can mesh the part into a quadrangulated mesh. This is going to enable us to export it as a step file back into the CAD package it came from, or we can run it and mesh it for another static analysis. So this is the topology optimized part after it's gone through the static analysis. We can see where the areas of high stress are. So from here, we might think this is okay to use as our final part, or maybe we want to go a step further and hollow the part because it's still well within our allowable stress limits. So we could hollow it to just a uniform wall thickness all the way around and run another static analysis on it, or we could do a variable shell, which we've done here. So this time we've shelled the part based on the results of that static analysis. So in areas of high stress, we've got a much thicker wall thickness. And in areas of low stress over here, we have a thinner wall thickness. Now, if we want some kind of crush resistance to the part, we can fill it with a lattice. And again, we're going to drive the beam thickness of the lattice from the results of our static analysis. So we can see that in areas of low stress here, we have a nice thin beam thickness. And in areas of high stress over here, we have a much thicker beam thickness to give a bit more support and rigidity to the part. Okay, so let's look at some more latticing options here. So this is an automotive headrest, just imported in again as a BREP model and converted into an implicit body. First thing we could do is a Reusable lattice. So this just takes random points within this mesh and creates beams between all of them to convert it into a lattice. And we can really quickly change the point spacing. If we want something with a bit more density, we can change that point spacing to make it a little bit smaller. In just a few seconds, that's going to come back with our result of this more dense lattice structure. Beam thickness, we've got control to change as well. We can also create a lattice from the mesh. So this is going to take the points from meshing that part and apply beams between all of those points. So it's a bit more uniform. And again, if we change our edge length to make our edge length a little bit bigger, we're going to get a lattice structure that's a bit less dense. You should expect with a mesh, we've got much finer results around these more detailed areas on these curves. And it's created a lattice structure from that. Now we also got the option of a variable density lattice. So here we have taken a point, this center point, and we've said to the lattice, we said that the lattice wants to be more dense around this point, less dense everywhere else. And again, thinner beam thickness close to this area, a thicker beam thickness further away. But if we want to move this lattice, if we want to move the point to change the density of the lattice elsewhere, all we do is drag and drop this point, and the lattice is going to update to have a much thicker density here and a thinner beam thickness. Let's go back to some topology optimization. So in this workflow, we have imported this CAD model. We've applied some restraint faces here, applied a load face here, a load force, material. In the workflow, we have set up a topology optimization. It's the topology optimized final part. And then from here, we've meshed this part again and run a static analysis to give our static analysis results of this part. Now we've got loads and loads of options that we can change in here. Loads of extra boundary conditions we can add, topology optimization constraints, and some options within the FEA as well, change material, edge length, etc., etc. So this is the full workflow that goes into building a topology optimization and a static analysis. But because we've created here a workflow rather than just a part, we can package all of this up into one really neat little custom block. So we're going to make our own custom block for a topology optimization and a static analysis. So these are the inputs that we want for our custom block. Force, material, edge length. We're also going to use the CAD body, restraint faces and load faces, and the result we're going to ask for is the static analysis result. So if we go to our next tab here, we have a completely brand new instance of nTopology. And in here, I'm going to import my custom block for topology optimization and FEA analysis. I'm going to use that same material that we had before, and I'm going to import the bracket, so the CAD model of the bracket. Now all this block is going to ask me for is a CAD body. So let's apply this CAD body. It's going to ask me for restraint face. Let's apply a couple of restraint faces. Let's make these two our restraint faces. It's going to ask me for a load face, and that's all it needs. So in the background, this block is going to take this model, it's going to mesh it, it's going to apply the restraint faces, the load faces. The load force is already pre-populated, the material, the edge length. It's going to run some topology optimization to get the topology optimized part. Then it's going to take the topology optimized part, mesh that, and give us a static analysis based on those results. So rather than that quite long detailed workflow that we had on the instance of nTopology before, we've now packaged all of that into this really neat little workflow here, with this really neat little custom block. And the beauty of this is that we can have a few of these going at the same time. So I can just bring in another topology optimization with FEA block. I can import a different CAD model. This time I'm going to bring that same bracket in that we saw at the beginning of the demo. Let's add in our custom block here. Drag this down into a new section. Again, all we'll need here is a CAD body. So let's create a CAD body variable, drag that into this block. It's going to ask me for some restraint faces. So let's apply restraint faces to here and here. And it's going to ask me for a load face, which will apply here. So again, we're going to have the same thing going on with this bracket. This custom block is going to mesh it, run the topology optimization, take the topology optimized part, mesh that, run a static analysis, and give us the results of the static analysis. So we've been doing that. This first one is now finished. We have the topology optimized result and an FEA view of what the FEA study looks like. So we can see the displacement, we can see the strain, we can see the stresses on the part. So you can take these results and decide whether we're going to do some further optimization, whether we're just going to take this part as it is, mesh it, and print it. So to print it, we can either export it in STL file to go into your slice data, slice software that you've got already. We've also got some slicing capability within nTopology as well. So in the manufacturing tab here, we've got some slicing options to slice the body, slice the mesh, and export it out in various different slice formats, ready to go to your printer. So in the background, the software is just running the topology optimization and the FEA study of this one. Let's just finish that now. And again, we've got the FEA results of the topology optimized part here. So stress, strain, and its displacement results. Okay, so another thing we're going to look at quickly is the texturing options that are available in nTopology. So I've got a couple of parts here. I've got this little kind of button CAD model and this bracket again. So we've got a few in architecture materials, we've got a few texturing options up here. So I've just dragged a couple of those and dropped them into this workflow down here. So the first one we're going to do is a Voronoi emboss. So if I just take my design space, drag it and drop it in here, it's going to really quickly create a Voronoi texture over all of that part. We can really quickly change this if we want a more dense lattice. Just up the cell count. We can change the thickness. We can also control the blend type between the lattice and the part itself. So we can have a 1 mil blend radius. We can make this chamfered, a sharp corner. Those are different options in here. We've also got again this Wi-Fi symbol on the thickness. So the thickness of this lattice can change based on some simulation data or just based on a point. It can be thicker in the middle and thinner as it goes further out, vice versa. And it's super simple just to change the body that we want to add the structure to. Drag and drop, and we've got our Voronoi on this bracket instead. Subtractive lattice, so worked very similarly. This time we're asking for a body. Again, I'm going to take my design space, and it's asking for a CAD face to subtract it from. So I'm just going to take the back face, this part here. This is a more uniform lattice structure. Change this, and it's going to give us really, really quickly the results of what that subtractive lattice looks like. We've also got the option to blend two different lattice types. So again, I'm going to take my design space and the back face of the part, and we are blending two together. So if I select 0 in this blend field, it's going to give us the lattice 1 type. If I select 1, it's going to give us the lattice 2 type. Again, we can change this to whatever we want to change it to. Now the blend field here, again, we've got the Wi-Fi symbol, so we can use a ramp block. So we can say at the bottom here we want one lattice type, and at the top we want a different lattice type. And it's going to slowly merge the two lattices together in the middle. And again, we can change this super quick by whichever two lattice types we want here. The wave pattern, this is a really powerful block. This is asking for a body to apply to here, and it's just going to give us a kind of a triangular wave over the body that we put into this block. So as you can see here, this is quite a simple version of it. It's just kind of running parallel to the part, but if we were to run it diagonally that way, and we can run a second one diagonally that way, we can get a really, really cool looking lattice, cool looking texture. So instead, I'm going to drag and drop this into our top of our workflow here. It's going to give us a 45-degree lattice that way, a 45-degree texture that way, 45-degree texture that way. It's going to come up with this as a final part. So something that would be super difficult to machine or to injection mold, but as a 3D printed part, you're probably not going to see a huge cost difference whether you're 3D printing this or whether you're 3D printing just the raw flat texture there. So you can really add a lot of value to a part really, really quickly with these texturing blocks. Another one we're going to look at here is the perforate block. Again, we just drag and drop the body into here, and it's going to perforate that whole body. Again, it doesn't matter which implicit body we use, just drag and drop. It's going to run those perforations straight away. And a leather texture. This is another really, really powerful block. You might have seen it on some previous videos that we've done for this leather texture block. all I do, drag and drop an implicit body. It's going to apply this really nice leather texture all over the part. And unlike some CAD softwares, it's just going to project an image of what it could look like. This has actually cut away all of these areas that need to be cut away to create this leather texture. So this part is now ready to mesh as an STL, to export to your slice data, or can just be sliced in nTopology, ready to go to build. Again, you can see the Wi-Fi symbol for the cell depth and the roughness, so we can change that from side to side, or if maybe we just wanted this face to have the texture, we can apply it just to this face using ramp blocks for our cell depth and our roughness. The frequency, we can make a more dense pattern or a less dense pattern really quickly. Cool, so the last couple of examples I'm going to show you is this is a bucket seat that's one of our colleagues at MSL. So this was scanned using our Creaform scanners. You can see the level of detail that it's able to produce on scanners. So we've taken the mesh and converted it into an implicit body. We've scaled it down and we have converted all of this surface of the seat into a lattice structure. We've driven the lattice structure based on some implicit models that we've put in here. So we're assuming that the kind of the spine, where your spine would sit in this seat, you want a more dense lattice structure with a smaller lattice thickness to give a bit more cushioning. Same in the areas of the sit bones, and then at the sides we want a bit more rigidity and more support, so we've got a much thicker lattice structure here. And we did something similar with this swing arm, which was scanned again using our Creaform scanners. Again, you can see the level of detail that's achievable from our Creaform scanners. This is brought in as an STL file, converted into an implicit body, and that's all we needed. We just needed the raw STL data from this. We've been able to run a topology optimization, Boolean back in all of the interfaces that we need for like the axles, the swing arms, where the bearings would sit, and these clips to hold cables, brake hoses, etc. on. And this is our topology optimized version of the swing arm. So one final part I'm going to show you is this another set of scan data that we've got this time of an arm. So you can see we've got two scan datas here. The orientation is very similar, but the positions of the fingers and thumb and the profile of the forearm is very different. Now in this workflow, we are going to take the scan data to the top of the workflow. We're going to convert it into an implicit body. We're going to create a surface lattice from that implicit body, add some bands at the extents of the cast, union everything together to create a cast that's completely conformal over the surface of the scan data that we had at the top of the workflow. So a really complex part to build, and we can really quickly edit this as well, so we can change some of the key parameters super fast. So for example, we've got control over the point count, so we can increase the density. We've got control over the lattice thickness, so at the moment those lattices are a uniform 2mm. I can increase those to a uniform 4mm. Maybe this increased lattice thickness is going to give a bit more stiffness to the cast, a bit less flexibility to get it on and off, so maybe we need this cut out to change from 5mm to 15mm. You can update that super quick. Maybe we don't want such a uniform lattice, maybe we want a thicker lattice at the kind of extents of the cast here and a thinner lattice in the middle. So I've got a ramp block already set up for that. I'm going to drag and drop my ramp block into the lattice thickness, and this is saying that from the cast extents, so from these bands here, at 0mm from those extents, we want the thickness to be 5mm. 50mm away from these extents, we want the beam thickness to be 1.5mm. So now we are going to have a result that looks like this. Much thicker beam thicknesses at the edges and thinner in the middle. Now we've also got control over the spatial weighting here. This drives the density of the lattice. So in this example, we might have an injury site that we want to have a more dense lattice structure around. So I'm going to drag and drop my ramp block into the spatial weighting here. This ramp block is going to take the injury site, so this implicit body here, that's the scalar field. It's going to say at 0 millimeters away, we want our lattice spacing to be 6 millimeters, and at 150 millimeters away, we want our spacing to be 15 millimeters. And that's going to give us a result here, where we have a more dense lattice structure near that injury site and a less dense lattice structure further away. So providing a bit more support and protection to that injury site and giving a bit more breathability and flexibility as we get further away from the injury site. Now here we've created a really complex model, a cast that's conformal to this surface, this scan data, varying lattice thicknesses, varying lattice densities. But if we wanted to apply this to another scan data, something that's going to be really difficult in a traditional CAD package, but because we haven't really created a part here, we've created a workflow. All we need to do is drag and drop our other scan data into the top of the workflow, and then Topology is going to run through all of those processes for us again based on this new scan data. Because the models are so robust and the workflow is so robust, it's just going to run through those processes again, and it's going to give us a result which is going to be the final cast with those same parameters that we've applied, but this time wrapped conformally around the surface of this scan data. So it's only going to take a few seconds to produce that. Here we go, here's our final result. So in probably 20 seconds or so, we've created the same cast but wrapped around a completely different geometry. And it shows you the power of just how quickly nTopology is able to produce and iterate models. Oh, so I think that's it in terms of demo. So if you guys have got any questions, then please feel free to stick your hands up and let me know.